This tutorial will guide you through setting up an EDEM simulation for an EDEM CFD coupling in a tablet coder. It will also cover the post-processing workflow for both AcuSolve and EDEM. When exporting geometry from AcuSolve to EDEM, all geometry parts will appear in EDEM, but we only keep the parts that are needed. Hold the Control key and select the unnecessary parts, then remove them. We keep the outlet parts only to identify the orientation of the tablet coder, although they have no role in the calculations. Select Outlet and Walls Outlet and merge them. Also, select Inlet and Walls Drum and merge them. Then rename the inlet part as Drum. Right-click on Geometries, choose Import Geometry, and load the baffles geometry file. Keep the default settings and click OK. Next, select Drum. Hold Control key and select Baffles. Right-click and choose Merge Geometry. You now have the drum and outlet geometry in your simulation. Save the simulation deck in the same folder where you saved the EDEM files. Also ensure that the API files are present, including the .dll file for Windows or .so file for Linux, the CUDA file, and the preferences text file for API properties. Right-click on Bulk Material and create a new material. Name this the spray material. Set Poisson's ratio to 0.25, solid density to 900, and shear modulus to 10 Pascal. Right-click on the spray material, go to Add Shapes library, and select Single Sphere. Set the physical radius to 0.0001 meters. Rename the particle as Spray. Then go to Properties and click Auto Calculation. Now create another bulk material and name it Tablet Material. Set Poisson's ratio to 0.25, solid density to 1400, and Young's modulus to 1 × 10 to the power of 6. Right-click on Tablet Material, choose Add Particle from Shape, and select Prism. Then right-click on the particle and rename it Tablet. Go to the Prism settings and use 0.004, 0.005, and 20 for length, radius, and sides, respectively. Then go to Properties and click Auto Calculation. Next, right-click on Equipment Material, add a new one, name it Steel, and set Poisson's ratio, density, and Young's modulus. Add the spray material. Click on plus again, add the tablet material, and continue until there are no more. Now go to spray material, click on plus, add spray material again, then add tablet material, and continue until there are no more. Then go to tablet material, click on plus, add tablet material, and continue until there are no more. Go to Physics, edit the contact chain, and add heat conduction and spray coating. Click on Heat Conduction, go to Settings, and set heat conduction coefficient for the spray to 0.5. Do the same for the tablet. For spray coating, go to Settings, add spray material, and click OK. Next, go to Particle Geometry, edit the chain, and add heat conduction and spray coating. Open heat conduction settings, set coefficients for spray and drum. Then set geometry temperature to 313. Do the same for the tablet. Click on spray coating, go to settings, add spray material, and click OK. Now go to particle body force, edit the chain, and add temperature update, then click OK. For temperature update, go to settings. For spray set 3800, and for tablet set 2000. Next, go to Geometries, right-click and add a polygon. Name it Spray Nozzle 1 and make it virtual. Go to Transform and set the position and rotation values. Open Polygon and set the number of edges to 25 and radius to 0.005 meters. Next, add a dynamic factory. Set the number of particles to unlimited, and the following factory parameters. Max attempts to 50, and choose spray material. For velocity, select spray, open settings, and set the direction as shown. Set the mean velocity to 5 meters per second. For temperature, set 293 Kelvin and click OK. Now right-click on spray nozzle, choose Copy Geometry, and select Single Copy. Then right-click, and rename the geometry to Spray Nozzle 2. Select Transform and set the X position to 0.05. Right-click on Geometries, add a cylinder, make it virtual, and rename it. Set the cylinder parameters for start radius, end radius, and length. Then go to Transform and set the following parameters. Verify that it fits inside the drum. Right-click on this cylinder, choose Add Factory, then Static Factory, rename it Tablet Factory. Set the total number to 6000. Make sure tablet material is selected. And set the temperature to 313. Now right-click on Drum, add Motion, choose Linear Rotational Kinematics. Set start time to 0.2 seconds. And initial velocity to -11 revolutions per minute. For the axis of rotation as shown. Use the Display Vector option to confirm the correct rotation movement. Choose Environment, and set gravity in the Z direction. Once you complete the model settings in the Creator, move to the simulator. Keep Auto Time Step, set Rayleigh percentage to 30%. Choose the CUDA solver, and save the simulation. Open AcuSolve, right-click on Results, and click Update, and confirm with Yes. Then right-click to view the solver log. You will see the solver is running. Finally, confirm the coupling server is active by checking the line that says Connecting to EDEM Successful. When the simulation is complete, you can return to SimLab to perform the post-processing for AcuSolve. This can be done by selecting Flow Post-Processing and clicking OK. To begin, create a cutting plane, select all bodies in the domain, and choose temperature from the list. Then change the orientation of the cutting plane to be normal to the x-axis. Enable the legend and reset the range. You can also enable vectors by selecting Display and then choosing Velocity Vectors. Set the vectors to have uniform size, not scaled by velocity magnitude, and apply a constant color. Then click OK. Hide the boundary collection so the results are clearly visible. You can also play the animation using the animation toolbar. Next, open EDEM to perform post-processing on the DEM side. For this, go to the EDEM Analyst. First, open Display Particles, select Tablets, and choose Color by Temperature to view the temperature distribution on each tablet. Enable Auto Update for the minimum and maximum values of temperature, so at every time step EDEM automatically adjusts the range to show accurate results. You can also display the spray and assign it a uniform black color for clearer visualization. Then return to the first frame and rewind the simulation. This allows you to observe how the temperature evolves on each tablet over time. To see the average temperature variation across all tablets, you can plot it as a function of time. To do this, go to Create Graph, select Tablet Particles, and for the x-axis set the range from 0.1 seconds to 120 seconds. Change the number of display points to 1000. For the y-axis, choose temperature as the primary attribute and set it to average. Then click Create Graph. This generates a clear plot of the average temperature versus time, showing how it increases and then reaches a steady-state condition in a periodic manner. For further information, please check the EDEM documentation.